Imagine you're building a personal assistant that talks with a user for weeks, maybe months. Every conversation, every tool call, every observation piles up into a growing interaction history. When the user asks something new, the assistant needs to reach back into that history and pull out just the right pieces of evidence. This is the agent memory problem, and it sits at the heart of any long-running large language model system. The dominant approach today is what you might call generative memory. Systems like Mem0, AMEM, MemoryOS, and others use the language model itself as part of the memory pipeline. They summarize past conversations, extract entities, build knowledge graphs, generate reflective notes, and update linked memory records, all by calling a language model repeatedly. The intuition is reasonable. If you compress and reorganize the past into cleaner abstractions, retrieval later becomes easier. But there's a hidden tax. Every one of those summarization or extraction steps burns tokens and time. And worse, when the model rewrites the past, it can drop details, merge distinct entities, or blur temporal updates. You end up retrieving from a lossy paraphrase of what actually happened, and traceability back to the original evidence gets weaker. The opposite extreme is to keep everything raw and just do lexical or dense retrieval over the full history. But that flat approach struggles when evidence is scattered across sessions or when semantically similar traces belong to different users or different points in time. The authors of Zero-Mem ask a provocative question. What if you could eliminate language model calls from the entire memory pipeline, everything except the final answer generation, and still get structured, high-quality retrieval? They call this regime zero-token memory operations. Nothing outside the final reader consumes a single input or output token from a language model. Encoder computation, meaning small embedding models and named entity recognizers, is allowed and accounted for separately, but the expensive generative work is banished from memory management entirely. Here's how they pull it off. Zero-Mem keeps the original interaction traces as the source of truth, never replacing them with generated summaries. Then it builds two complementary views over those traces. The first is an entity context graph. They run a lightweight named entity recognizer like SpaceEye over each chunk of conversation. And whenever an entity appears in a context unit, they add a weighted edge. The weight is essentially the frequency of that entity in that context, normalized. They also connect adjacent context units so local continuity is preserved. Think of this graph as a map of who and what shows up where, built purely from observation rather than from a language model's interpretation. The second view is a temporal hierarchy that organizes the same traces at multiple granularities. Individual turns, short windows, longer episodes grouped by semantic and temporal boundaries, and local spans that preserve immediate neighborhoods. Both views point back to the same original text, so provenance is never lost. When a query arrives, Zero-Mem builds a small deterministic profile of it, extracting the subject, keywords, expected answer type, temporal cues, and any boundary information. This profile decides how to route the query. If it's a relational question that needs connecting facts across the history, the graph view gets more weight. If it's a local question about a specific session or recent state, the hierarchical view leads. Both views actually run in every case. The profile just controls the weighting during fusion. On the graph side, they match query entities to observed graph entities, propagate activation through co-occurrent sentences weighted by dense similarity to the query, and then run personalized page rank to spread evidence across the relational structure. On the hierarchical side, they do course-defined search, first identifying relevant episodes, then narrowing to windows, then to turns, and finally expanding to local spans when surrounding context matters. Both views produce rankings, which get normalized and fused using the routing coefficient. Then comes evidence closure, which supplements the top candidates with related graph neighbors and adjacent turns, so the reader sees not just isolated snippets, but connected, contextualized evidence. The last non-generative step is deterministic evidence calibration. Zero-Mem filters out candidates that violate provenance or boundary constraints, ranks the survivors by subject, temporal, and answer type compatibility, and hands a compact evidence set to the reader. The reader is the only place a language model gets called. After the reader produces an answer, one more deterministic pass checks whether the answer is actually supported by the evidence, whether it matches the expected type and format, and applies things like list pruning or extractive shortening if needed. The whole pipeline is like a well-organized library where librarians who don't need to read every book can still find you exactly the right passages. And only when you want a written synthesis does an author get involved. The results are striking. On Locomo, a long-term conversational memory benchmark, Zero-Mem beats every baseline including GAM, the strongest prior system, by about 5 F1 points on average with both GPT-4o Mini and QN 2.5 14B. On Hotpot QA extended to context links up to 448,000 tokens, it wins across every context length and every reader, averaging about 5.5 F1 points over the best baseline. But the efficiency numbers are where the paper really lands its punch. GAM consumes about 28 million tokens on memory operations across the benchmark. Simple Mem consumes about 14 million. Even Light Mem, which was designed for token efficiency, still burns nearly 900,000 tokens. Zero-Mem consumes 0. And it's not slower for the trouble. Total memory operation time is under 6 minutes, or about 0.22 seconds per query, which is a 57.6% reduction relative to Light Mem, the fastest baseline. Ablations confirm that both views matter. Dropping the graph or dropping the hierarchy each hurts significantly, and removing evidence closure or calibration also degrades performance. Now, some honest limitations. The system leans heavily on the quality of the off-the-shelf named entity recognizer and dense embedding model. In domains where entities are ambiguous, jargon-heavy, or where relationships between entities need genuine inference rather than co-occurrence, the graph view could get thin. Zero-Mem also can't consolidate contradictions or update stale facts the way a generative memory system can because it never rewrites the past. If a user says something in session 1 and contradicts it in session 5, Zero-Mem retrieves both and hopes the reader sorts it out. There's also a subtle bootstrapping cost. The query profile extraction is deterministic, which is fast but potentially brittle for queries that don't fit clean patterns. And while the paper reports impressive latency numbers, the encoder computation, PageRank propagation, and multi-granularity indexing are non-trivial at truly massive scale. Still, the broader implication is provocative. A lot of the field has assumed that better memory means more sophisticated generative processing. Zero-Mem is a strong counterexample. Preserve the source, build good structural indices, and let structure plus retrieval do the work. Now let's walk through some questions you might have after hearing all of this. First, why does having two separate views, the graph and the hierarchy, work better than just picking one really good structure? The intuition is that different questions need different kinds of context. A question like, when did Alice mention the merger, needs temporal locality and session state, which the hierarchy captures naturally. A question like, what connects Alice's project to the Berlin office, needs relational bridges across many turns, which the graph captures. Neither structure alone can serve both patterns well, and the fusion step lets the query itself decide the balance. The ablation showing significant drops when either view is removed confirms this isn't just architectural decoration. Second, isn't the query profile itself doing something almost like language model work when it extracts subjects, keywords, answer types, and temporal cues? How is that free? Good catch. The profile is built deterministically from the query using pattern matching, part-of-speech heuristics, and small non-generative encoders, not by calling a large language model. It's cheap and fast, but it's also less flexible than a language model would be. For clean, well-formed queries, this works fine, but for ambiguous or unusual questions, the profile might misclassify the routing, at which point Zero-Mem relies on the fact that both views still run and both contribute to fusion. So bad routing degrades performance gracefully rather than catastrophically. Third, what would happen if you scaled the interaction history to truly enormous sizes, like years of conversation with millions of turns? The graph and hierarchy would both grow, and personalized page rank on a huge graph gets expensive. In practice, you'd want to shard the graph by session or by time window, cap the propagation depth, and maintain approximate page rank with periodic offline updates. The temporal hierarchy is already amenable to this because episodes and windows give you natural sharding boundaries. The core insight, that structure plus retrieval beats generation, still holds, but engineering it at planetary scale would require the usual bag of tricks around index sharding, incremental updates, and approximate top K search. For large-scale recommendation systems serving hundreds of millions of users, the ideas here map surprisingly cleanly onto some core pain points. Think about long-term user modeling. Today, systems that try to build rich user representations from months of interaction history often lean on expensive language model calls to summarize user interests, extract preference profiles, or generate synthetic user descriptions. Zero-Mem's argument suggests you could instead maintain an entity context graph over user interactions with items, creators, and topics, weighted by observed co-occurrence, alongside a temporal hierarchy that captures session-level intent and longer-term drift. When a candidate retrieval or ranking query comes in, you route between the relational view, which finds items connected through shared entities and behavioral bridges, and the temporal view, which captures recent context and session state. All of this can run at very low latency because there's no generative call in the retrieval path. More concretely, this could reshape how you build the user-side tower for retrieval or the context features for ranking. Instead of periodically running expensive language model jobs to refresh user embeddings or generate profile text, you maintain lightweight, provenance-preserving structural indices that update incrementally as new interactions arrive. Real-time serving benefits because deterministic evidence calibration is much faster than any generative post-processing. And provenance preservation matters for recommendation systems too, both for debugging why a particular item was recommended and for regulatory and trust reasons where you may need to point back to the exact interactions that drove a decision. The core lesson is that in high-throughput systems, generative memory work is often a luxury you can't afford, and structured non-generative retrieval over raw traces may be a much better fit for the latency and cost envelope of production recommenders.